Hello, thanks for coming. Those of you who were yesterday at Bezat's defense already know Chris Kiefer, but I will give him a brief introduction. Chris is a professor at the University of Sussex, where he teaches musical instrument design, and he's a researcher in the Experimental Music Technologies Lab, where his work focuses on music and AI, on interaction and music instruments design, and in particular, in hybrid musical instruments with embedded AI. And that's, in fact, what he's going to talk today, I think. He's also a performing musician. He plays an augmented self-resonating cello as half of the improv duo Feedback Cell and with the feedback drone quartet Brain Dead Ensemble. And he's also a live coder and solo artist who performs under the name of Luma. Luma? Luma. So today he's going to talk about the Musically Embodied Machine Learning project, which is currently running at the University of Sussex, exploring the challenges and creative opportunities that arise when instruments become hybrid and when AI becomes embedded in the instruments. Thank you.
Thanks, Sergey. Thank you for coming. So I'm going to talk about this project today. These are the things I'm not going to talk about, just by way of introduction. I'm from this place, University of Sussex on the south coast in the UK. And apart from this project, which I'm going to discuss, I get up to really involved in feedback, making feedback instruments, which are instruments that usually self-resonate or have some kind of recursive process in. So there's a music release that just came out, which is all made on feedback instruments, and we ran this network a couple of years ago exploring this. Also running a little modular synth company at the moment called eMeet Lab Instruments after our research group, which is a sort of way of commercializing or just getting our research out into hardware, out into the world. And this is a module we just put out called USeek, which lets you live code in your modular synth. So I'm not going to talk about those, but if you're interested, you're welcome to ask. So this is the project. This is an 18-month project, which is funded by the Arts and Humanities Research Council in the UK. So I'm working on it. We've got Andrea Martelloni, who's a research fellow, and also Nick Seymour-Smith is a research software engineer in our school, so he kind of contributes to the technology. And this is running till roughly next October. And what it's all about is thinking about what's the expressive potential of machine learning when it's kind of tightly couples with musical instruments. So just by way of kind of rough ideas, these are the kind of things that people tend to use machine learning for creatively. So maybe processing gestures. Machine learning is really, really good at capturing gesture through various devices. It's pretty good at useful for designing mappings, so taking gesture and being the black box in the middle between some kind of input and sound synthesis. It's pretty good at sound synthesis as well, or kind of abstract signal processing processes, and also pretty good at generative, either pattern symbolic or audio production. So those are the kind of things people tend to use machine learning for. I mean, there's plenty more than that really, but maybe that's the core things. But there's also a lot of wider possibilities around machine learning. And I think I'd go out on a limb and say that the main reason I'm interested in machine learning is a way of creating complexity in musical instruments. So to me, it's sort of a means to an end. It's when we're building instruments which have computing in, computing's natural tendency is towards linearness and dryness. And machine learning is a really interesting or useful way at the moment of creating some kind of organic musical feel in musical instruments and giving them a bit of agency and a bit of life of their own. So I think that's the bigger picture for me. But also, I'm really interested in how we can adapt musical instruments. So if a musical instrument has got some sort of AI, I'm going to call it machine learning, not AI, machine learning process inside it, that is a malleable thing. So how can instruments adapt over time? Maybe some ethics issues there around how data kind of evolves within a musical instrument and models. Machine learning is a really good way of opening up complex processes to musicians who don't have technical experience. So we can program musical instruments in Max or SuperCollider. That takes a lot of know-how. With machine learning, we can program musical instruments by example. So by saying, if this happens, I want this to happen as a result. And so that process can become musical because collecting training data can be a musical process. It also offers ways of creating shared agency between humans and machines. So the machines with machine learning can have some sort of life of their own, so they're not just linear processes of human movement. And then we've got intrinsic creative possibilities of machine learning that have arisen just out of the technology. So things like latent space exploration in generative systems, and network bending, which is the kind of machine learning equivalent of circuit bending, where you reach into networks and mess around with their parameters, see what happens. So there's a bunch of new affordances which come out of these technologies. So what this project is responding to is a bit of thinking about the problems with how we use machine learning in musical instruments. And quite often there's this pretty disembodied split between an instrument and the way that we create models. So the standard way that we go about creating models is very technical. So we tend to use Python notebooks or some kind of laptop or desktop. There might be GPUs involved. It's data science. It's not something that musicians tend to do on an everyday thing. So a typical thing might be that, say we've got this cello on the left here. Say we want to get this cello to have a process in there that responds to some gesture that the cellist is doing. So the process would be to record some data of the cellist moving about, and then take that data into a data science environment, train some models, come back, try them with the cellist. And then so you've got this really long loop, and this disembodied split between something that's very musical and something that's very technical. So this project is about trying to think about this machine learning process holistically and think, how can we close this gap, and what happens if we build these processes into musical instruments. So zooming right out, just thinking about kind of creative machine learning generally, this is the usual situation that we're dealing with. We've got some kind of tunable, optimizable process. That process is embedded in an environment. So that environment could be sensor data from a person or an instrument, could be the internet, could be many things. And we've got a human involved, and that human is running some sort of optimization process and gradually tuning that model until it does what we want to do. On top of that, we've got some sort of task which might be tightly defined, like I want to recognize hand gestures, or it might be loosely defined. We might just be evolving a model until it does something that feels right, but we're not quite sure what it is. And this project is trying to focus on this whole process, so not just this tunable model in the environment, but thinking about this whole optimization process and how the human is involved in that. So we're investigating this thing called, this is a horrible acronym, I haven't found a better word for it yet, but instruments with tunable machine learning. So tunable is the key thing here. We're not worried about static pre-trained models. We're trying to think about malleable machine learning models and how they can evolve with instruments. So building machine learning completely into a musical instrument and having the interface for training and running inference on that model built into the instrument. And so the idea is that if we can build all of this into the instrument, can that process become musical instead of this disembodied kind of data science music split? There's a few implications for that if we're going to build machine learning into a musical instrument, we need to start thinking about low power computing. So this is interactive machine learning. It's not big data, it's very small data. We need to run things on possibly computers that will run on battery power. So GPUs are going to be out of the question. So bigger models like transformers would be quite challenging to use in this situation. We need to think about how we can simplify the way that we train models so that we can have controls on a musical instrument that will do that. So going from having all the options that you have in, say, PyTorch and finding out how we can restrict those so we can run them with hardware controls. And then thinking about how these instruments adapt and evolve over their lifetimes as musicians kind of personalize them and adapt them in different directions. So these are our research questions on the project. So we're thinking about musical practice. So how do musicians respond to playing these sort of instruments? Thinking about machine learning processes, and thinking a lot about technology and how we can design the interfaces and design the models that are next to these interfaces. Thinking about playable feel as well. So ergodynamics, that comes from Thor Magnusson's book, Sonic Writing, and it's the kind of musical equivalent of gameplay feel. Thinking about how the feeling of an instrument is. I've got a couple of example instruments that follow this sort of approach. So the first one is from Rebecca Febrink and Letitia Tsunami, and this one's called a Spring Spire, and it uses Rebecca Febrink's Wekinator system in the background, which is a tool it's very useful for designing parameters, parameter mappings. And so Febrink and Tsunami wrote this really fascinating paper where they've been working together for 8 years, longer now, from 2020, and they interviewed each other about how this process has evolved. And Tsunami has some very interesting thoughts about how this was really useful for mapping. So she's saying here, mapping is the backbone of composition. It bridges the physical world to the sonic world. ML offers a way to easily configure mappings with a wide variety of behaviors, thus allowing the composer to focus on the sounds and compositions. And she says, I cannot envision at this point in time any other ways to map. So this kind of strongly hints at the way that we can train by example in machine learning. So in this instrument, there's kind of transducers and springs, and it feeds sound through the springs, and you can squeeze the springs around to change the sound. So it's obviously quite complex data coming out of this instrument. And so she's using machine learning to map that data into sound synthesis. Another instrument that's a bit more recent is Gianluca Elia's digital no-input mixer. So Gianluca was a master's student on the Sound of Music Computing in Copenhagen, and he made this really wonderful instrument, which is it's the digital equivalent of a no-input mixer. So it's a feedback system, but it's digitally controllable. So there's a bunch of VCAs in this box, and then the circuit equivalent of a no-input mixer, and you can digitally control this. And so what he did was he wanted a way to control this pretty complex parameter space, and so he introduced machine learning by mapping between a grid and some parameters, so he could kind of morph across parameters in this no-input mixer. So another example of taking something that's a bit messy and complex and using machine learning to take this complexity and kind of structure it and order it. So that's a good use case for machine learning. But both these instruments are instruments that have machine learning in the background, and training these instruments is part of the way you compose and perform with them. They don't use static pre-trained models. So that's the kind of area that this project is in. I think it's important to talk about methodology and how we're running this project. Our main idea at the moment, and I think probably where we're going to get the most valuable data, is we've got long-term participatory design studies with musicians. So we're paying a couple of musicians to be co-researchers on our project, and we're working with them to kind of build instruments. So we're just starting to work with someone next week who is a vocalist who does a lot of looping, and we're going to design an instrument with her which uses some sort of machine learning, some sort of malleable machine learning. We don't know how it's going to go yet, so the idea is it's really emergent. We're just going to explore different prototypes with her and gradually build an instrument that she's going to go and rehearse with and perform with. And through that process, she's going to give us a lot of in-depth feedback about this process. So we've got a good chance of getting some really rich data there. We're also working with probe instruments, which means we're building a load of kind of fairly cheap, small instruments and giving them out to people with the idea that they'll document their process in a bit more of a lightweight way and feed back to us. We're running workshops. We're just about to go to Copenhagen next month and run a PhD course on this topic, and we're collaborating with IAL over in Reykjavik. We're also following autobiographical design, and if you haven't heard of that, the idea is slightly going against some conventional wisdom in HCI, where the user is always right. But if you're, for a designer, you tend to have some very in-depth knowledge and intimate knowledge of the instruments you build. So why throw that away? And so if we admit that experience is very subjective, but still possible to get some research insights from, then what we do is kind of structure the process of designing an instrument and document it really thoroughly, and then reflect on that documentation at the end of the project. So I'm building my own instrument as part of this. Andrea, our research assistant, is building his own, and we're going to kind of get into depth and hopefully get some insights back from that. And then the final thing is we're collaborating with Schlappy Engineering, who are a modular company over in Portland in the US, and we're looking at how we might find something that could be a product for them that involves the techniques that we're developing on this project. Also, we might put some of these things out through our own company as well. So hardware. I'm going to talk about the technical side for a little bit. So if we're building instruments with machine learning embedded, we need to move away from this because it's noisy, it uses lots of power, won't run off a battery. So we can't do stuff in the cloud either because there's loads of latency in accessing a cloud. We don't want musicians to have to worry about Wi-Fi when they're playing their instrument or something. So we need to move towards this right-hand side of the spectrum, thinking about microcontrollers, maybe even FPGAs as well. So thinking about how we can get high-power computing running inside musical instruments. And there's another open question, which I'm not really sure, related to this, which I'm not really sure about the answer yet. But we're thinking about what's the value of having everything self-contained in a musical instrument. And kind of thinking about when we work with participants, that they've got this artifact, which is the instrument, which evolves in its own right, and it doesn't have to be connected to something else. It doesn't have to be a collection of technology that's inconvenient to use. So we're thinking about what's the value of actually building these things in a self-contained way. So part of this, we've latched onto this technology called XMOS. XMOS is a microcontroller which is sort of super-powered. It's got 16 cores on it. It's like having 16 little ARM chips in one chip. It costs about the same as an ARM chip, so you get quite good value for money. It's quite challenging to develop with, we found out. So if you've used microcontrollers and maybe you've worked with Arduino or Teensy or Pika or something, then you're in this very supported environment, and there's nice forums to ask people about problems, and there's technology and good documentation. XMOS is it's an industrial chip, and it comes with all those issues that a lot of people who've worked on this it's proprietary technology, so you can't find many good examples around on the web So it's actually, we're discovering, not the best thing for a research project, because we have to spend a lot of time messing around with this thing, and it does things like go wrong and not tell us why, kind of just panics and crashes, which isn't very helpful. So as a prototyping tool, it's tough, but when it works, it's really, really good, and you can get all these cores and run some machine learning models on one core and synthesis on another core and so on, so and machine listening on another one. So it's very powerful, but it's bloody hard work. So we're also working with this new thing as well, the RP2350, which is a lot more user-friendly, and thinking about using this to prototype and then maybe transfer onto XMOS when things get working. So things like this can take 3 minutes to compile the firmware for. So if you're prototyping, that's really, really annoying, where the pico is 5 seconds. We're developing this MLP library for microcontrollers, which we've kind of developed from another project. So that's on GitHub. Our GitHub is Musically Embodied ML. We've got a bunch of evolving software on that website. The machine learning technology we're using at the moment isn't that advanced or particularly interesting, because we're more concerned about the whole processes that surrounds the machine learning rather than the machine learning itself. So we're using pretty vanilla multi-layer perceptrons, nothing too exciting technologically in that way at the moment. So what I'm going to talk about is show you some practical examples of what we've been up to. And we went to a little 1-day or 2-day workshop last weekend and ran a workshop on our project there and did some demos. And as part of that, we tried to take a lot of the tech we've been messing around with and put that into practice for people to try out and get some feedback. So just returning to this question, which this is the main thing we're thinking about at this workshop: how do we embed training inference into musical instruments in musical ways, and what kind of workflows are valuable around that? We took a fairly vanilla machine learning or kind of musical process as a test case for this, and so kind of mapping with large parameter spaces. So this isn't a particularly new thing, it's been around for a long time, but the idea is you have some kind of input, complex input, it goes through a mapping process, and then you have some sort of process with lots and lots of parameters which you're transferring that data to control. So it's a kind of small to many mapping processes. And you could kind of hand code that, you could write some stuff in Max or SuperCollider to do the mapping, or you can bung a neural network in the middle. And if you do that, then you can start creating the mappings by example instead of hand coding them. So you can collect pairs of inputs and outputs and then get the neural network to learn those relationships in the middle. So it's a nice use case for machine learning. And what we're really interested in is the whole processes that happen around this. So thinking about how you curate data and how you train the models and how you just explore these parameter spaces and find salient, interesting musical things within them. We built 3 instruments for this workshop, 3 variations on this parameter mapping theme. So these are all really rough and ready, and we're probably going to take them apart and turn them into something new after these workshops, so they're sort of temporary. But this is the format they followed. We found these really nice 3D joysticks online, so they're left, right, up, down, but you can also twist the top of the joysticks, so they're kind of used for industrial control. You've got this extra button on the top. So they're quite nice tactile input devices. People might use them for moving cameras around or something like that. And then we made various variations on the theme. And then in the back here, we've got an XMOS dev board that's coupled with a PiPico Wi-Fi board that handles the interface elements. So this is all pretty rough and ready. This is not a great way to build things, but I'd always rather get a PCB made, because this wiring always tends to go wrong after a while, but sometimes you just don't have time for PCBs, so that's what we had to do. And part of this project actually is thinking about decent prototyping techniques. So how do we build instruments responsively and really quickly, but in a way that's reliable and that they don't fall apart. So when we're doing participatory design with musicians, we're going to need to keep building new things and trying out different ideas. And there's not always time to go through kind of formal, like good engineering processes. So how do we do it roughly in a way that's hopefully a bit reliable? The first one of these instruments then is a FM synth. And this is it's got a MIDI keyboard plugged in. And the idea is that you map from this joystick into a much larger parameter space on FM synth. I've got a video of an earlier prototype of this one here. So the idea is at the moment it's just recording training data and mapping, making connections from joystick positions in the FM synth. And then that's training. Then once you've done that, you've got this point space that you've got to explore. So there's a bit of toy example that our new one you could actually play with melodies, which is a bit nicer than that one there. The second one we built was something that interfaces with Eurorack. So this uses a Euclidean sequencer. And if you don't know about Euclidean sequencing, it's a way of making rhythms with a couple of hyperparameters. And the idea is that you have a number of slots for beats in a circle, and then you specify the number of beats you want, and it tries to fit those as evenly as possible into the circle. So we have 4 of those running at once, and you can also control the speed and offset of these Euclidean generators. And so that gives you a parameter space of kind of 16, of which you get all these varying rhythms when you mix these things together. And so with this one, you can plug it into different bits on the Eurorack and cycle through some rhythms. Also got a video of this one. This is Eric Schlappi, our industrial collaborator, a little while ago with an earlier prototype of this. And so he's kind of playing techno with this thing. And he's set up some different rhythms in the space in the joystick, and he's playing just by scrolling around in this 3D space. And then the last one we did was a multi-effects unit. So audio input, audio output, and in the middle there's an effects unit. It's got 4 effects, some delay, flanging, ring modulation, filtering, and they're all connected up through a mixing matrix, which is also parameterized by the neural network. So they're kind of all interconnected, and there's low levels of feedback going through this thing. So you end up with quite a big parameter space in this one. It's got something like 30 parameters which parameterize the effects settings and also how signals flow through between them. And then you can train different areas on this joystick to respond to different effects. So I think we also... Actually, I don't know what happened to the video of that one. Maybe it's here. Oh yeah, so this is a prototype. So as you move around, you can kind of move between reverbs or different combinations of effects in different areas of the joystick. But in a way, the actual machines here aren't the main aim of what we're doing. We're just trying to build machines to get a feeling for how the machine learning processes work. So this is all a means to an end, really. So the question is, how do we train these models and curate these models in a way that's musical? Let's think about the data then. What we're essentially doing with these models is creating pairs of joystick XYZ with a bunch of DSP parameters on the other side, which is either effects settings, Euclidean settings, FM synthesis parameters. And we're trying to get a collection of these pairings and use them to train models. And so what we initially did was just do random, we started off with random exploration of these parameter spaces. So we got these pretty big, I think anything with more than 4 parameters becomes a large parameter space and kind of complex to explore. And so we got these quite large ones with 15, 30 parameters, which, and initially we're just exploring them randomly, kind of jumping about, finding good points, and storing those in the data. But we started to explore more musical ways to do this instead of just rolling the dice all the time. And so we started using neural networks to actually do the exploration for us. And so in the top right here, we've got the process is we have a joystick. So we have exploration mode, basically, where we're collecting data, which we're going to train the model with. And the joystick is mapped through a neural network, just a randomized neural network initially, and that's mapped out to the DSP. And we explore that space with a joystick, and then when you find something you like, you press a button, and it retrains the neural network to center on that point. And we have an exploration range, and so you can slowly start to zoom into this parameter space and find the kind of salient things that you like. And so the process then is we randomize, we explore, zoom, and kind of hone into where these interesting settings are. And then we store this data point and then start back at another random point. And at any point you can switch between inference and training and kind of test out how these things work in your instrument. We ended up building a web API for this, just so we didn't want to put the controls in hardware yet. So we just made them in software so you can hook up to the Pi Pico in the instruments with your mobile phone and get some extra controls. And so there's a bit of data curation here. So you have 4 models, and you can choose between those models, and you can train different ones at different times. You've also got 4 data sets, so when you're collecting data, you can choose where to store that. And then once you've got this, you can then start to train models with different combinations of data. So we start to get a bit creative with how we can evolve these models. And we can also choose how well or badly we train these models. So sometimes badly trained models sound really good. And you don't really know that's part of machine learning, that you get happy accidents and something might sound really good with not much information. So we have a way of controlling the number of iterations that you apply data to the model with, and monitoring the loss as well as you train the model. So the idea is you can get a model and kind of pull it around in different directions until you're settled on a set of mappings or a model that you like. So I think we call this structured exploration of parameter spaces. So it's trying to think of a way to get these massive parameter spaces and interact with the machine learning or through machine learning to kind of narrow these spaces down into something that's interesting, and do that in a musical way. So these are some of the themes that have come out of the workshop last weekend that were most salient, really. So we're thinking a lot about shared agency and how much you can control that. Some people commented that they felt like the instrument was controlling them as much as they were controlling the instrument. And maybe that's a good thing, actually. We have that a lot in feedback instruments. There's this concept of unmastery. So instead of this classical model of top-down virtuosic control of an instrument, we let the instrument guide us. So the analogy could be surfing. So we're kind of working together with another object, and we find what we want to do musically together. Then we talked about serendipity a lot. One of the really nice things about machine learning is that it tends to surprise you in non-random ways. So of course, if something random happens, pure randomness can sound horrible or noisy or jittery. But when machine learning does not what you're expecting it to do, it sort of has this tendency to happen in a musical way. So you can get some nice surprises. And I'm not sure exactly mathematically why that tends to happen. That's just an intuition, really. So we're thinking about how you can control the temperature of this level of surprise and have neural networks which are kind of linear and predictable, or if you can warm them up and get something a bit more lively out of them, just like you could a feedback instrument. Especially with the multi-effects, we're really thinking about how you can encourage sparsity, especially as applied to parameter space exploration. So when you've got a lot going on, and sometimes it's quite difficult to hear the differences between different parameters, because you've got this nonlinear system in the neural network, and then you've got nonlinear system in the multi-effects, and then it's difficult to figure out the relationship between the two. So we're thinking about how to enforce the neural networks to have sparse outputs, so it's quite, when they control something, there's wider difference between what they're in the settings that they're creating. Pretty interesting theme that came up was scaffolding. So when we're training neural networks, a lot of the skill involved in these particular systems is in recognizing sounds. And so you move to a certain place, and you record some data, you place it in the 3D space, and then maybe you want to come check that it's trained properly. So you have to remember that sound and check it's still there. And that's actually a bit of a skill. And so how can we add feedback? People talked about labeling different settings just with random words to see if that would help. Can we use color, audio visuals, or something like that to help just give some extra cues into how we sculpt these parameter spaces? And thinking about the affordances of machine learning. I can't remember what I meant by that. No, I can. So we've got these kind of raw things going on in machine learning. So this interface here, it connects you to the real low-level stuff, thinking about models, data sets, thinking about loss functions and iterations. And there's lots of creative possibilities there, but is that too much for some musicians? Would it be better to package these up into kind of meta processes, and so it's a bit less scientific, a bit less technical, and a bit more thinking about metaphors that control these processes instead. So that was the outcomes of this workshop, and stuff we're going to feed into the next iterations of how these instruments evolve and how we're working with participatory design with musicians. And I just wanted to comment on just the last few slides about some of the things that we're thinking about working on in the next 10 months. So the first one is thinking about machine learning approaches. At the moment, we're just using a super vanilla multi-layer perceptron because we're interested in what goes on around it, not the thing itself. But of course, the thing itself can be really interesting. So we've been looking up a lot about reinforcement learning, with the idea that with reinforcement learning, you can have some kind of agent in the instrument which is going around collecting training data for you. And then instead of actually getting involved in this sort of messy process of data curation, we can just be telling an agent, I like this, I don't like this, or go in a different direction and try something new. And so maybe there's some agency in the instrument which supports this, which is a bit sort of dry and technical. Also really interested, and always have been, in the idea of reservoir computing. Reservoir computing was kind of more popular in the 2000s, maybe early 2010s. It's a bit less common now because it got deep learning came along and works a lot better in some ways. But still, for signal processing, these things are really good. So this bottom right diagram here is a generic way of thinking about reservoir computing, where we have some sort of input, and then we have a non-linear dynamical system which you perturb with your input data, and then you monitor the reaction of that dynamical system with a neural network, and by training just the output layer, the neural network, you can create mappings. So by observing how this dynamical system gets perturbed. And what the nice thing is about these things is that time is built into the model. And so the dynamical system, by definition, has a timely reaction to the input. And of course, in a musical instrument, what we want is a really nice way to encode or have a timely reaction to something. And so reservoirs are very good at that. They're a bit tricky to use. The other nice thing about them is, I mentioned network bending earlier, which is the machine learning equivalent of circuit bending. So getting neural networks and finding salient ways in which they process data and messing around with them to change their behavior and see what happens. And so with these reservoirs, they're really open to network bending. You can kind of apply gains to different areas of the network, so you can suppress them, you can feed extra signals into them, and they'll do possibly interesting things. And then the last thing we're interested in is differentiable logic. Differentiable logic is a way of doing super optimal computing on microcontrollers. And what it is running neural networks not with conventional nodes, but just as using binary logic. And so you binarize your data and feed it through a bunch of logic gates. So the logic gates create a nonlinear mapping, and then you get your output on the other side. But of course, logic gates aren't differentiable because they're either on and off. There's not continuity between them. But a researcher in the US, Felix Peterson, found a really nice system for making these logic gates differentiable. And so what you can do now is you can create a training data in PyTorch, you can train one of these diff logic models, and then you can export it to C. And then you can run that on an Arduino or a microcontroller. And these things will run millions of hertz, because there's nothing, they're just like 500 logic gates or something like that. And so it's a really nice way of taking something complex and running it super fast on low power computing devices. But they're not trainable, you can't train them on device, but we're thinking about how they can be part of a bigger network, so we can train them to do a certain function like make a sound. People are using these for chiptune at the moment, or recognize a gesture, and then have some extra trainable network layers surrounding those. So that's the ML side. And then a couple of instruments that we're working on. So the multi-effects unit I mentioned earlier, I've been talking to a producer at Sussex, and we had an interesting conversation about how that could fit into studio production workflow. And the idea is that we can customize one of these multi-effects units to do the same thing as a channel strip. So it'd have a bunch of EQs, have a compressor, have some, maybe some sort of warm distortion on it. And then our collaborator is going to try think about how to use this as part of a mixing workflow, say for mixing voice or mixing guitar or something, and thinking about how you can adapt and train and store models which are really, really good at processing certain instruments, and then have some kind of variable control or gestural control of these processes. So kind of the opposite to having lots and lots of scientific style knobs to package this stuff up gesturally into a machine learning machine. And then the last thing as part of this autobiographical design process is I made this feedback instrument a little while ago here called the Z3, which is it's a 2-string bowed instrument. It's made out of bamboo, and it's got a couple of pickups on. The sound goes out and goes through some processing, and it gets fed back into a transducer on the front there, and the whole thing self-resonates. So it has a bit of a kind of life of its own. It sounds quite industrial. And I'm really interested in building machine learning into this instrument. I'm thinking about how it could be used for customizable machine listening to recognize either sounds or patterns or behaviors which are occurring in the feedback loop of this instrument, and then modulate the behavior of this instrument in response to those patterns, and how that could become part of a performance or a part of way of kind of composing an instrument, maybe. So, yeah, that's it. Thanks, and have you got any questions? Yeah.
This is regarding the joystick control FMC.
Yeah.
I wonder, no, I don't think it's just a few of us. Hi there. I'm a master student here at the MTG. And the question is regarding the joystick controlled FM, the FM controller.
Yeah.
I wonder if you prototype this in software. Like, I would love to have a go at it, like, even though I don't have the 3D controller. I'd love to use like a XY pad and see what the results sound like, let's say in a software synth.
Yeah.
So have you done something like that? Like, or is there any publication for this work?
Yeah, actually, there is the example I showed is oh yeah. The example that I showed is pretty tightly coupled with the XMOS stuff. There is another example of that, which if you know SuperCollider or happy to run SuperCollider scripts, we've got a SuperCollider version which responds to mouse and does a similar thing. So if you email me, I can send you the script if you want to try it out.
Yeah, because recently I have been playing around with Flucoma.
Yeah.
And it lets you run very simple MLP networks inside your DAW.
Yeah.
So I wonder, thinking about this concept, how powerful would that be, running an ML model to generate sounds in a stock FM synth? So it'd be nice, like, if there was sort of like an open source mapping of, a model, and the mapping to an FM synth, for example, because FM synths are the same, right? Like, depending, you can use anything. So,
yeah.
I mean, I'd love to see how, how that result would sound, even in the software.
Yeah.
Sort of domain.
Yeah, actually, the example I've got uses Flucoma already, actually.
Oh,
yeah.
Nice.
Which is a great system. And the nice thing about FM is you can just stack up lots of operators. So these systems, you could run it with 100 operators, and it would still be the same process. It just you can scale it up quite nicely to get more complex sounds.
Hey, thanks a lot. It was really interesting. I resonate with a lot of ideas that you have mentioned, so I could actually ask multiple questions.
Okay.
But I will try to focus maybe on two that interest me the most. So first of all, the network bending. It's something that I myself experiment with in the course of my PhD. And what interests me in what you have said is that it's an equivalent of the circuit bending. And I have never really heard someone talking about it this way. Because from my experience, network bending comes more from the ideas, the founding ideas of the network bending come from the visual domain, where perhaps the instrument design is not like a widespread discourse or paradigm. So this comparison to the circuit bending, I have never encountered before, although myself, I also do like to compare it to it. Although I guess the difference is that, at least in the papers that I have seen on network bending in the visual domain, what they try to do is still somehow approach the topic theoretically and find scientifically founded operations that can be conducted on the networks, while the circuit bending is like this very anti-theoretical thing, right? That the idea is that you can just open an instrument, short circuit randomly, kind of just taking notes of what works and what doesn't.
Yeah.
How would you? How do you feel? Did you actually? Do you have some experience with network bending, or did you have a chance to approach it? What would you say about it?
Yeah, I think there's various ways you can approach it. Are you thinking about the Terence Broad's paper?
Yes,
Yeah.
exactly.
And so there's another paper also from Matthew Yi King, where they did circuit bending, network bending with DDSP.
Okay.
And so I think it was from AIMC a couple of years ago, so that might be worth checking out. But I think there's really some different ways you can think about it. You can, of course, just take a completely random approach and say, well, here's my network of weights. I'll just throw stuff at it, or maybe I'll mute that bit and just see what happens. But you can also think about watching the network and looking for saliency. So you might build a heat map of how the activations work in the network over time, and think, okay, well that's a hotspot. Now I'm going to feed a signal into there, or apply some manipulation to that salient point, which is more likely to have an effect than somewhere that's not hot in the heat map. So I think there's loads of different ways you can think about structuring or doing that analysis when it's musical, using machine listening or frequency analysis of activations or something like that.
Yeah, cool. What was the name of the paper that you have mentioned?
So it was on DDSP, and it was from Matthew E. King and someone else who I can't remember.
Okay, I'll try to find it.
But if you can't find it, send me an email.
Yeah. So maybe like following the topic of this maybe theoretical versus anti-theoretical. You also mentioned the autobiographical approaches.
Yeah.
I'm also curious about what is your experience with that, and what are the challenges of doing research that is based on your own insight? How can you legitimize it in the eyes of the research community, for example? What are the methods that actually render the research valid for you? Or general thoughts on, because I don't think that it's also it's a pretty novel approach, right? So I think it's still very experimental, so I'm very curious to...
Yeah, I think that the first paper about that was, I think, 2013 or something. And so there have been various discussions, academic discussions about it. But yeah, this idea that the user is always right, that's fine, but I think it's equally fair to say that designers do have an intimate knowledge of the things that they build. And it seems a shame just to throw that away, especially as in research terms, we don't often get into that sort of depth with people who are playing instruments, which is why we're doing long-term PD on this project. But I think the key to this whole thing is rigor and structure. So if you're going to report on your own experience, you have to first say that, okay, this is a really subjective thing. Whatever I'm saying is not generalizable knowledge, but that's still useful because it can become part of a wider conversation about a particular topic that other researchers can pick up on. It can stimulate other research ideas in other places, but we're not trying to generalize. And I think often in musical instrument design research, we're not looking to prove hypotheses either. There's not necessarily a right answer to anything in musical instrument design. We're more interested in seeing what creative opportunities arise from different, trying to find new ways to make music, which people have always done. And so to that extent, there's no reason why very subjective data can't be part of a design process. But if you're going to try and add some rigor to that, then the idea is to be rigorous with documentation. So as I'm doing an auto-bio design thing, I'm gonna keep everything about my process. So of course all my source code will be on GitHub. I'm gonna be taking lots of photos. I'm gonna be keeping all my schematics. I'm gonna be having a diary which documents everything that went wrong and everything went right. And I'll probably, every kind of salient point in the process, I'm going to sit down and reflect on what I'm doing. And so when I get to the end and start to report on it, I've got all this data, which then I can think about in a structured way, which is trying to get away from just getting to the end and writing down your opinions, trying to be a bit more organized and structured and formal about it.
Okay, yeah, great. Thank you.
Cheers.
Hi.
Hi.
quite interested in the feedback instruments that you've built in the past. And you mentioned at the end this stringed instruments that you plan to incorporate some machine learning process in. In the context of these feedback instruments, I'm wondering if you could just speak a little bit more on what you envision for the training process or compiling data, or what the goals of the data will be, and more on that.
Yeah, it's an interesting question. I think for me, in my experience of playing feedback instruments, the goal is always to find some way to shape their behavior in a musical way. So what the instrument that I showed there, and numerous other feedback instruments, their default mode of behavior is if you just switch them on and turn up the gain, they'll settle into some either pattern of silence or screaming. And what's actually interesting musically is when they kind of get warmed up just to the edge of feedback or just around the edge of chaos, and then they tend to do interesting things. But if you push them past there, then they saturate, or if you don't go there, if you don't put enough energy into them, then they don't do interesting things musically. So in the past, I've made various systems to try and get in this, what you might call a golden zone, kind of edge of chaos, and get to stay there. So we've done some stuff with doing complexity analysis of the signals coming out of the instruments, and then modulating gain based on the complexity of the signals. And I think machine learning, and this is speculative because I haven't done it yet, but I think machine learning is going to be quite useful in that sort of way of getting to this like golden zone, because it's going to offer a way of kind of training mappings. The very basic thing, you could have machine listening in a model which will detect, sounds that you don't want, and then change the instrument accordingly. But then I think it could become a lot more interesting that if you get it to respond to sounds which are in your kind of golden zone, then you might be able to navigate around. A lot of what goes on in feedback instruments is about moving between attractors, basically. So you have trajectories between attractors. Some of those are bad attractors that are unmusical, like silence, but some of them are really interesting, and sometimes you get into the states they're kind of hopping between attractors, which can be quite satisfying to play. And so I'm hoping that machine learning is going to have some way of helping support the instruments get into those areas and then stay there.
And I guess that could be expanded a bit more, not just modulating gain necessarily, but other things within the loop.
So it could be modulating saturation, it could be introducing new sounds into the instruments, some sort of generative synthesis. It might be changing the mappings and, for example, filtering the information that's incoming from the strings. It could even be looking at the acoustics of the instrument, so maybe having contact mics or measuring vibration instead of sounds and responding to that instead.
Cool, thanks.
Cheers.
I've got a question about what you sort of think of the lifespan of these models within instruments, and whether, some of the examples you talked about, especially the earlier ones, you sort of reset the model and retrain, and so they're kind of they have a kind of shorter lifespan. But in some of the feedback instruments, do you sort of envision using these in a kind of, you never reset the model and they kind of continuously train, and then they kind of they come to embody a sort of more long-term identity for that instrument?
Yeah, that's a really interesting question, and I think something that we're going to find out about over this year. Let's say you've got a guitar, electric guitar, common instrument, and you got some sort of machine learning process running in there. Maybe it recognizes some gestures in the sounds, and you slowly adapt that so each time you train your model, maybe you've got a bunch of models running this guitar that change the behavior of the guitar in different ways. Then, first of all, you get a sort of ethics dimension here, because that's your instrument. What happens if you gave that instrument to another guitarist? Would it be very much adapted to the way that you played it, much more than just the hardware of the guitar? So I think it's very open questions. What happens if you lost the data of that? What if you had a SD card crisis and then you've lost the instrument in a way? So that's another kind of more pragmatic issue in hardware. If you gave it to someone else, would you just reset it, start again? If someone stole it, what would that mean? I don't know. So that's something we're exploring, and I think I think we'll find some interesting things about it. But for now, it's just speculation.
I could ask one more question that you mentioned affordances in one of the slides. And you also mentioned something along the lines that when the machine learning algorithm fails or does something random, it tends to be musical somehow. There's sort of like an intuition behind it, right?
Yeah.
Well, I also have similar intuition, but I feel like very difficult to actually document it or or leverage it. And I feel like it links a bit to this idea of the affordance, in the sense of like what does the machine learning algorithm afford over like other approaches, for example, random approach, right?
Yeah.
There is also this thing that sometimes with these models trained on such subjective data and tasks, it's kind of difficult to differentiate, or like, because like all the evaluation methods they're based on the user studies, right? So it's all just trying to see how specific instrument can be applied in practice, right? But then I just wonder if you have thoughts also of whether there are ways to approach this topic from more theoretical perspective. Do you think about how could this specificity of the machine learning and the affordances that it provides, how can they be theoretically documented?
Yeah. And you could get into some math analysis of why this intuition might be true. And I think the starting point, and I'm just really speculating here, is that a neural network is a nonlinear projection from input to output. And I can't remember the name of the theory, but it gets used in similarity search, that if you have two spaces that are close in the input space and you put them through the same nonlinear projection, they tend to be close together in the output space. And so once you're projecting data through this, putting data through this projection, if you have undefined behavior, it's going to tend to be in the same area as the other stuff that you're putting through it. So that maybe that's where I'd start. If I could remember the name of that theory, I can't.
Yeah, but that's a nice direction. But do you think there is something very, I don't know, specific to the ML process that makes it different than other kind of processes?
Yeah, I see what you mean, because you could just put anything through a matrix, right, without machine learning. Yeah, that's a really good question. And I guess the difference between machine learning and other similar mathematical processes is that it's customizable, and that you can take a creative way of optimizing these things by example. So maybe that gives us a chance in user studies for people to use these systems and then give some feedback from a non-technical point of view about that. So maybe that's the affordance that opens up.
So it would be like the context that actually makes it special, or like the thing that it's being applied, and there's a human that collaborates with it.
Yeah, maybe that's the particular affordance of this.
Okay, yeah, thanks.
Yeah.
Thank you very much, Chris, for
Thank you.
a very inspiring talk.
Brilliant.
There were not many people, but as you've seen, I think we were all really with the questions.
Yeah. Yeah.
I will make you a question.
Okay.
You mentioned in the examples in the joystick exploration, have you used machine listening to look for sweet spots or for special areas?
No, not yet. And that was one of the plans we had with the multi-effects unit, but we didn't have time to do before our workshop, that we'd also be not just feed forward modulating the effects in the mixing matrix, that we'd be learning how the part of the learnt parameters would be how the effects responded to machine listening processes, or putting machine learning through as part of the input parameter space into these multi-effects. So yeah, that's something we're really interesting to explore, and that's something I'm quite interested in terms of this feedback instrument as well. So creating effects mappings that are audio reactive and responsive. But also coming back to this idea of sparsity, it makes, with all this stuff going on, it's I think the challenge there is to how you explore those big spaces because when the actual thing that you're trying to map to becomes much more nonlinear and complex, and then trying to get a complex process to match up with that becomes exponentially complex. And so sparsity would be the key to... Does that answer your question?
Yeah.
Yeah.
Thank you.
Cheers.
So if there are no more questions, so thank you very much.
Thank you. Thanks for coming.